Alright, here we go, guys. So today we're going to do problem of the day for December 9th, 1339, maximum product of splitted binary tree. It's a medium problem. I've never done this problem before. So let's see. Given the root of a binary tree, split the binary tree into two subtrees by removing one edge such that the product of the sums of the two subtrees is maximized. Return the maximum product of the sums of the two subtrees. Since the answer may be too large, return it modulo 10, 9 plus 7. Note that you need to maximize the answer before taking the mod, not after taking it. Or maximize the answer before taking the mod. Okay, so it says we have this tree here, and we're going to split it between these two edges, and we sum these numbers inside. And then we multiply them together such that they are maximized values. Same thing here, sum 6 and 15, and we split it here. That's the maximized quote-unquote sum. Okay, so we could have the number of nodes in the tree is 2 or up to 5 times 10 to the 4th, and the node values are 10 to the 4th. Okay, so before we do anything, let's, of course, write down everything we've seen here. So what's the goal of this? The goal is to produce the max sum of a binary tree in which you split it into two subtrees. The max product in which you multiply the sums of two subs. That's essentially what's happening. So inputs param1, root of the tree to split. Output, return the max product of the binary tree split into 2 modulo 10 to the 4th plus 7, 10 to the 9th plus 7. Okay. So let's talk about some examples. So here immediately, where would I split it? I could split it here, and if I split it here, I have the sums 2 and then the sums 4, which gets you 8. Or I could split it here, which is going to be it's going to be, what is this? 3 times 3 is equal to 9. Okay. So let's think about this for a second. How many edges do I have that I can split? If I have 3 nodes, I actually have n minus 1 edges. So if I have n nodes, I have n minus 1 edges, and that's possibly n minus 1 products to try, right? We have 2 to try here because we have 3 nodes. So if we had 5 nodes, we would have 5 minus 1 edges, which is 4. And so that we have 4 different quote-unquote edges to split from and 4 different products to basically get. So the question is, do we need to try every single product? Is there some sort of heuristic we can use to reduce the amount of products to try? Not off the top of my head. I do notice, though, that if the two numbers are closer to being equal with each other, they're typically going to be a bigger number. For example, 2 times 10 is equal to 20, but if you were to split them half and half, so it becomes 6 and 6, you get 36. So generally, sums that are closer equal to each other are going to be just as big. But unfortunately, in our binary tree here, we don't really have a strong way of finding these sums that are quote unquote equal to each other. So we will probably have to try every single edge and receive every single product. So just doing that alone is going to be O of n time complexity. So that's pretty good considering what's at stake here. If there's like a logarithmic, I think the next time complexity that would be faster is log, or possibly square root. But since we're dealing with trees, I'm looking towards a logarithmic time complexity. And nothing is coming to mind at the moment, because a logarithmic time complexity usually means you're able to use some sort of optimized search. So it's like we're able to search for the correct edge to remove. But honestly, since the tree is not organized in any certain fashion or way, there's no good way to do that. You are probably just going to have to try every edge. So with that in mind, the next question is, how do we do this without having to recalculate the sum every time we split an edge? For example, if I want to, on this example 1, have the 1 and the 2. Let's say I wanted to split it between the 1 and the 3. Well, that means I have to traverse this whole tree again just to calculate this subtree. And then I have to recalculate this subtree. And then let's say I want to try the split between 1 and 2. Now I have to recalculate this subtree and then the 1, 3, 6 subtree. And if you might notice that there's like something highly unoptimized here, because we're repeating calculations, right? So we do something like a prefix tree. I think that would be the most optimized solution if we just go through it once over and calculate the tree with prefix sums. So for example, this node, instead of a 1, it's now replaced with the sum of everything, all the descendants below it. And so alongside with this one, so alongside with all the descendants below it. And so every time we split, we can just say, okay, now this, we know the subtree is going to be the sum of all the descendants below it for 2, this node. And then this subtree is going to be the sum of all the descendants below it minus the child subtree that it's detaching from. Does that make sense? I hope that makes sense, what I'm saying. So we can try to transform this tree into a prefix sum, kind of taking ideas from, you know, the array solutions before. And so that would be O of n time. So let's, just for being thorough about this, let's write this. Calculate tree with prefix sums, sum of all descendant nodes below it. Can use DFS for that. And then try every tree split using DFS, take the max sum. Now the issue is you know, how do we do this in C++? Because what the product's way too big, right? It says I have to return it modulo 10 to the 9th plus 7. I might have to use like a long integer or something like that, or something that can handle very, very large numbers. It's all positive numbers, so I could use unsigned long integer or long to get bigger, but I'll have to look that up for me to continue off that. So yes. Okay. Let's go ahead and calculate that prefix sum. Now, what could happen here is that I create a completely separate tree from it, or I reuse the tree we have here. Now, typically, it's not in good practice to modify the parameters of a function, but in this case, since I want to have a very optimized solution, I'm going to go ahead and just reuse the tree. So let's go ahead and, well, I guess for LeetCode's sake, I would reuse the tree, but in a technical interview, you probably want to create your own tree. Okay, so in that case, am I practicing for LeetCode or for technical interview? Let's pretend this is a technical interview. So I'm going to go ahead and create my own tree node. The prefix sum root equal to new tree node. Okay. Then we are going to have a DFS function. So in DFS, we'll take in a tree node current, and we will calculate this DFS. This is DFS for the sum, taking the sum root. I had to do that. So what we want is, oh wait, we need to take in, also want to take in, this is a sum cur, and then we're going to have the cur. So we're taking the root. Okay. So sum cur val is equal to cur val plus dfs sum cur new node cur left plus dfs sum new tree node cur right. See if cur return 0, otherwise return some cur value. If cur left, not cur left, and not cur right, then sum cur val is equal to cur val. Else we're going to let's do this. This is some tree node, some cur left, and then we'll have the right. Then we need to attach them, right? Some cur left, some cur right, and we'll say some cur left, some cur left, some right, some cur right. Okay, so we're going to attach them, and oh, wait. We should have if statements. Else, if cur left, then we create this node, then we attach this node, and then otherwise, let's do this. If some, let's do this. Yes, that's a lot cleaner. If cur left, if cur right, and let's say some cur plus equal dfs sum cur left, cur Okay, so this makes a lot more sense. And basically all I'm doing is saying, okay, create that prefix sum. If it's not there, just return 0. That's fine. Well, I should always have a node, so I don't think I need this check. Let's just say this. Okay, pass a new tree node. Set it equal to the current value and say, okay, then add the descendants values if it does exist, add the right descendant values if it does exist, and return now the sum. So now that's the DFS sum. That should set up the sum root. Now all we need to do is go through every single possible max product. So now it's DFS product, tree node, sum current. I guess I could pass in the max product. Let's do that. Int max. Int max product 0 DFS product sum root and then the max product. We talked about this though. CPP long biggest integer data type. Biggest number long data type. Unsigned long. $64 bids. 2 to 64. Okay, now we have our unsigned long in. Now we want to pass that in, and then we're going to say detach it, right? Max product, so product. So max product. Max product. Let's call it that. Okay. Now we have our DFS of max product. Now we have to split them up. So sum cur, if sum cur left, then we need to say product is equal to max of product and sum cur left val times sum cur val minus sum cur left val. Okay. And of course, let's parentheses this. The same thing for if there's a right. If sum cur right. Void. And of course, defects, max product. If there is a left, we'll just throw in the left and the product. And of course, there's a right, then we throw in the right. Okay, and then int modulo is equal to, let's see, CPP exponent exponential power. How do I do the power operator? Yes, pow. Okay, it's CMAF pow. It's equal to pow 10, 9 plus 7. Let's say unsigned long int return max product modulo. Okay, so that should be it. Now, before I run it, let's run through this in the test case. So first things first, I create my new tree node, plug it in, bam, bam, some root. I say some root is now equal to 1. Okay. If there's a left one, then I will create a new tree node. I will point it to that tree node, and then I will say, now DFS that sum. And I go again, I say now this is equal to 2 plus the DFS of this number, so now that, and now I return a 4, so that's 6, again with the right, so plus 6, 5 is 11, up the tree, now that's 12, now I check if there's a right to that one, so that's good. So that creates the sum root, that's good. Now the product, I put in my prefix sum tree, then I say, okay, if it has a left tree, try splitting that edge and take the max product of it. So I take the left times itself minus the left, so that's this tree. And then I continue on that branch. Now I split the left, check the tree. Oh, wait. Oh, no. Oh, okay. So I actually caught a mistake here. So this, if I split this tree off, it's not this subtree. It's the whole thing minus this subtree. And if I did the same for let's say this one, it's the whole subtree minus this subtree. Okay, so I need the root. Tree node root. So some root. And then some root. So the root value, root. So here, if I split off here, it'll be this left value times root minus this value. And that makes sense. And the same thing here, root. Okay, that makes sense. And then modulo, okay. Now if I run it, it should look good. No max. Unsigned long, that's right. Where do I wrap this unsigned long? And I wrap it like this. Right, and you pass the root, pass the root. Undeclined, oops. Okay, and that is it. Let's go ahead and submit the code. Take us to the next page. And it's accepted. It beats 82%, but it takes a lot of memory. How am I doing on time? So that's 25 minutes, and I was taking a little bit of time on that one. Let's take a look how they handled the big numbers in the CPP solution. They just use longs. Right, that makes sense. Okay. So I guess this could just be a long. Let's try converting it to a long and see if that's any faster. So long, long, long. Probably be a little better on the space. Wow, okay, so it didn't do that much better, and it's actually slower, huh? Let's see the solution in Python. Yes, O of N, and then the space is O of H, correct. Oh, that's a gorgeous one. Total is equal to S root, comma S root. If not root, return 0. Left, right is equal to S root dot left. S root dot right. Self dot result is equal to max self res. Left times total minus left. And right times total minus left. Oh, he does it in the same pass. Oh, he's so smart. So you have to calculate the total first. So that's what this is. And then on the second pass, you start calculating. Ah, gotcha. But this is a little convoluted in my opinion. You could just do it in two separate functions. It's easier to read this way. But honestly, impressed. Okay, that's 1339, maximum product with splitted binary tree. Hope you enjoyed the video, and hope to see you next time.